So the next part that I want us to take a look at then is the macroscopic properties that is affected by the intermolecular forces. So the first one that we have to pay special attention to is molecular size, which will become very important once we start dealing with organic molecules, so during this year and also in grade 12. Now here they tell us then that alkanes are a group of organic compounds. Now what's very important about these organic compounds is that it's carbon atoms linked together to form long chains. So for instance here, the little black circle represents the carbon atom, the little white circles represents hydrogen atoms, and then that little molecule there is methane that we've been working with quite a lot. And we could go on 2 carbon atoms surrounded by hydrogen, and that's your ethane. And then we have 1, 2, 3, 4, 5 carbon atoms surrounded by hydrogen, so that's your pentane. And we have 6 carbon atoms, which is your hexane. And then also we have icosane, that massive molecule at the bottom. Now, what's important is that as the length of the chain increases, the molecular size and surface area of the molecule also increases, which becomes very, very important, because the larger the molecular size and the surface area, the more places there are for London forces to actually form. The example that I'm going to use here is I'm going to just use our methane as an example so that we can take a look at these spaces that forms. So when we take a look at the methane molecule, we know that it's a carbon atom and the carbon atom is bonded to 4 hydrogen atoms. We also know then that when we take a look at our electronegativity of our hydrogen, we find that the electronegativity of our hydrogen atoms is 2.1, whereas the electronegativity of carbon is 2.5. So in each one of these carbon-hydrogen bonds, we find that the difference in electronegativity is simply 2.5 minus the 2.1, which gives us then our 0.4. It's a very, very small difference in electronegativity, but it is still a polar covalent bond. Okay, that means each one of these 4 hydrogen-carbon bonds is polar covalent bonds. What's important then is if we take a look at the difference in electronegativity between the hydrogen atom and the carbon atom, we can go and we can see that the carbon atom is stronger than the hydrogen atom, meaning that the shared electrons in each one of these bonds will spend more time around the carbon atom, okay, making the entire outside of this molecule slightly positive and making the carbon atom on the inside slightly negative. Now with our rule, there's no way we can draw a line through this molecule to find a definite opposite positive and negative side, so we have a non-polar molecule. Okay, so that we can go and we can say we understand that methane is a non-polar molecule. Okay, now what does that mean for us when we're taking a look at a methane molecule interacting with a methane molecule? So when we have 2 methane molecules interacting with each other, so let's just draw 2 little methane molecules here. Okay, and there is our 2 little methane molecules. Now we know that both those molecules have got a slightly positive exterior, okay? But when we're dealing with this induced dipole forces or London forces, what happens is that the shared electrons are kind of forced towards one side of the molecule, creating a slightly negative side and creating a slightly positive side, which then in turn allows these actual two non-polar molecules to bond to each other. It's very important to remember that these are incredibly short-lived forces, but they're short-lived forces and they're not very strong. But if we take a look at bigger molecules, and let's take, for example, let's use here our pentane and our icosane. Okay, so if we take a look at pentane and icosane, and let's say they interact with each other the way they're printed here, and we say, let's say a London force forms here and here and here. Because of the larger size of the two molecules, we don't just have one London force forming, but three. Okay, and the larger the molecule becomes, the more London forces we have that form. So yes, London forces are weak forces, but because we can have multiple London forces between two molecules, they add up to a very, very strong intermolecular force. Okay, so let's compare those molecules to each other. So here we then have our methane, ethane, pentane, hexane and icosane, and as we can see, as we move from the smallest molecule to the largest molecule, we get a massive increase in molecular mass. And as the molecular mass increases, we can immediately see there is a decrease in the melting and the boiling point, because as the molecule increases, there are more forces holding the molecules together. Therefore, more energy is required to break the bonds between the molecules. And in grade 10, you learned that temperature is a measure of average kinetic energy. Okay, so it's very, very important to remember that as the melting and boiling point of a substance or a molecule gets higher, it means more energy is required to actually break the bonds between the molecules and to allow it to undergo a phase change. So the next property we want to take a look at then is viscosity. Okay, now viscosity is the resistance to flow of a liquid, and here we can compare water and syrup to each other. Okay, so let's say for instance you have a glass of water and you have a glass full of syrup. Okay, if you take the glass of water and you stir it, it's very easy to stir. Okay, where syrup, it's kind of, you can feel it's more sticky, it's more thick, it's difficult to stir. Okay, same with if you take the glass of water and you throw it out, it just leaves the glass very easily, whereas the syrup sticks to it and it's stringy and it's thick and it doesn't really want to flow. Okay, now what's very important to understand with viscosity, and we mentioned it in a previous video also, is here we're dealing with those two forces. Now we're dealing with adhesion and cohesion, where adhesion forces is the forces between the liquid and the sides of the container that they're in. In other words, the force of attraction there, whereas cohesion forces are the forces that we find inside our substance. In other words, the intermolecular forces. So all we have to remember is that the stronger the intermolecular forces are, the more viscous the substance is. In other words, the higher the viscosity of that substance is. The next one then, density. It's not something you've done in a while. You learned about it in technology. Density is the mass per unit volume of a substance. Okay, and that is probably the best example we have. If we have a cork and a rock of the same size, exactly the same size, and we throw them into water, the rock will sink, whereas the cork will float. Now, why is that? And that's also got to do with intermolecular forces. The stronger the intermolecular forces in substances or in between molecules are, the closer those molecules will be pulled to each other and the more dense they will become. Now, when we say something is more dense, we just mean we have more particles in the same space compared to another substance. That's why we express density as mass per unit volume. Okay? Excuse me. So if we take a look at the example on this side, we have three liquids. We have oil, water, and syrup. Okay, so if we throw all of the liquids into a glass, the syrup will immediately sink to the bottom of the glass because it's the most dense. There's the most particles per unit volume. whereas the water will go and lie on top of the syrup because it's less dense than the syrup, therefore it floats on top of the syrup. The oil will then float on top of the water because oil is less dense than water again. Now if we throw in some solid materials, we throw in a cork, the cork would float on top of the oil because the cork is less dense than oil, less dense than water, and less dense than the syrup. If you throw in a plastic Lego block, it will sink through the oil because it's more dense than the oil, okay? But it will float on the water because it's less dense than the water. If you throw in a grape, then it'll sink through the oil and the water because it's more dense than both those liquids, and it will float on the syrup because it's less dense than the syrup. So in other words, the stronger the intermolecular forces, the closer the molecules are pulled to each other, and therefore the more dense the material becomes, the more stuff we can have in the same unit volume. Okay, melting and boiling point, we've already discussed this. General rule of thumb for melting and boiling point is that the stronger the intermolecular forces are, the higher the melting and boiling point is. And if we compare any substances to each other, usually melting and boiling point is the first thing we take a look at, because if we know a substance has a high melting point and a high boiling point, we already know there should be very strong intermolecular forces involved. Then we get to two very interesting topics: thermal expansion and thermal conductivity. Thermal expansion is something that materials does when they gain energy. Now earlier on I said that we define temperature as a measure of average kinetic energy. Okay, so substances is heated, or when substances is heated, their molecules start moving faster. This causes the substance to expand. Okay, that's why we have those little gaps on bridges, and even if you look at some buildings, we have building gaps there that allows for expansion. The reason we allow for this expansion is if you think of the tiles in your bathroom or in a kitchen or so on, the reason we leave those little gaps between them is that when the material expands, they push against each other, and if there wasn't any place for expansion, they would push against each other so hard that the tile might break, that the tiles might lift up, and so on. Okay, if you've ever been lying in your bed late at night and you hear these weird squeaking sounds, it's not because of a bad monster hiding in your roof, it's because the house was in the sun the whole day. The roof, the bricks, everything expanded. And we're not talking about expansion in the terms that a one-bedroom house turns into a two-bedroom house. We're talking about very small expansion, but still enough for the materials to scrape against each other. Okay? At nighttime, the house releases that energy out into the environment again, it cools down, it shrinks again, and the materials scrape against each other, and that's that sound you hear. Thermal conductivity then is basically why materials conduct energy. Now, for a substance like a metal frying pan to be thermally conductive, means it has to absorb a lot of energy and transport that energy to every single molecule in, or that makes up that pan. Okay, we can't do this with all materials. We already know that we make use of metals for this because metals have extremely high melting and boiling points, therefore very strong forces holding them together. Okay, so when we heat up the material gets energy, and they start vibrating and push on the atom next to them and next to them, and so on. The energy spreads throughout the material.